cloud. Okay. Do you guys see the thing? Like,
Yep.
Okay, for anyone watching this recording, I'm very impressed that you found this and wanting to watch it. I don't think anyone watches recordings. I was just talking about GCC, it's the GNU compiler collection. So the topic of this first hour is how do we get from code to something that can run on a compiler or that can run on a processor. So this is what I'll be using. This is Windows terminal. Like if you have like command prompts, like command, okay, or PowerShell, like all of these are, I think, fine. Zoom is causing issues, but yeah, so you just need a terminal interface. So I'm gonna be using Windows terminal. I'll close this one. And then like when you first start it, it'll look like this. And I've installed Ubuntu. Hold on. I need you guys to see my search bar. And right now my search bar is only showing up on my window. Let me think how I can resolve this. Can you guys still see stuff? Oh, no, okay. Let me reshare. Okay, so I'm just duplicating my screen. So I have my laptop down here, then the big TV, and you guys can see both. So you should have some version of Ubuntu installed. This is just the Linux distribution that we're going to be doing our demo through. So I have it here. This is well, go away. Okay, this is the how do I, okay, whatever. But this is Ubuntu. Like you can see that it's this one, and then it's grabbing some other stuff. So is everyone here so far? Like you guys have a thing open and you can like you have Ubuntu? Yeah. What about people on the, okay. Yeah, I can't see the oh yeah, so like apt or advanced package manager, I think, is like the install thing. So it would look like sudo apt install neo fetch. Sudo is like to run with like admin privileges, but I already have it installed, so it's going to say like, oh, you don't need to install anything. Okay. So within, trying to make this like friendly for people. Just give me a second. So this is like my files on the Windows side. So just open up like your favorite text editor, and open up that same folder. Like this is the UTAT demo folder. Open up the same folder in terminal as well. So like, did you guys know what I'm talking about? Like just go somewhere, create a folder, and then I think like you should be able to just right click and then open in terminal if you have it configured. Like, are people there? Okay, so this is like a technicality that I have to explain, I guess. So when I first launched this is Windows terminal. I can do like Windows stuff. II means open folder, so it means like open folder here. But you may also be doing this where you just launch directly into Ubuntu, in which case this is like you're stuck in Linux land, and this won't work. So yeah, so I just quit out of it. What I do is, like, I'm in Windows right now. If I do bash, this opens up Ubuntu, and this is like Ubuntu stuff, and then I can exit out of here, and now I'm back to Windows.
Okay.
So like starting from here, you know, just go like, I don't know, like, do I have a temp directory? Like just make some random thing, open it. And then you can, you know, from here open like Notepad or like whatever text editor you want. And then at the same time have bash open or yeah. So this is my, like, we're gonna work through and create all of these files are like through the thing, but if I do an ls, okay, let me make it nice, like ls, you can see like my main.c, my main dot, like all of these files are here. Do a make clean out. Yeah. Okay, is everybody there? I like, I have no feedback. I don't know. Oh. Well, what about the people on the call? Like, because I can't see their faces. I guess there's nothing to see anyway, because no one turns on camera. So
Are we supposed to have these files already or no?
no. Like, I could give it to you guys. Like, I think they're pretty short, so we can just write it like write it line by line. You guys follow along. Yeah.
Okay.
I don't think so. What? Does anybody know how to do Mac OS stuff? I think because Mac OS is a Unix-based operating system, you don't need to install Linux. Like, you should be able to have GCC. Like, do you have terminal? Like, or whatever, that ZSH or whatever they call it, or yeah, what do you have open right now? Console maybe? I don't know what they call it. Well, yeah, because that's Windows. Yeah, you terminal. This will be okay. Okay, yeah. So this is fine. This, like, yeah. Like, you have what is needed. But open up like a text editor. So okay, so let's let me just start fresh. Data demo fresh. Oh. Okay, so this, you guys should see something like this. So just create a file, call it like main.c, and save it in that folder. So here, main.c. And then I just want to have a basic function just to print something. So like int main void printf hello world. Like, this is like the most basic function, like most basic C program you can have. And then, oh, we need a return because we're good programmers and everything should have a return statement. And then I'm going to include the standard IO library, which has a function definition for printf. Like, let me know when people are here, and then I'll go on to the next one.
Yep, I'm good.
Well, what text editor do you like to use? like when you're writing code? Like no. Pardon? Can you open that? Or like, are you here or?
No, I press LS and now there's a bunch of this control C at the top.
Yeah, so it's by default, it starts up in the Windows folder, so there's a run stuff. Type CD, space, folder. So that means home, like the home directory. Yeah, go there, and then you can do it.
Thank you.
With no template. Maybe download Sublime text for. I'm gonna tell you what I use because the thing that it looks like it tries to package together a lot of things. So when you click the magic button that says run, it does all the things behind the background and you won't be able to see what's going on. Specifically, I'm trying to use like terminal utilities to show you exactly the steps that are happening. Yeah, just open it like on shape. And then file or file, open, and then select a folder where you want to work. Yeah, just make a new folder called like yeah. Are people on the call somewhere close to here?
Yep.
Who is that? That's it? Yeah. Like okay, I can't like see.
Mark here.
I'm gonna join on my iPad so I could see people's faces. The password 361053.
Recording in progress.
Okay. Okay, are everybody?
I'm in my like the UTAD demo directory then. I'm gonna open up the code and
What code editor? I think it's just code. Like that's a or just open up Visual Studio Code and then navigate to like through Visual Studio Code.
okay.
Because you gotta do some configuration stuff if you want to just do it. Which is not hard, it's faster. What are you doing? Or like this, sorry, like maybe I should explain like C code because most people are just finished first year. You guys took a programming course, right? Oh, in Python. Oh, well, this is not Python. Python's higher up than C, so like there's stuff that you might not see here. So like your main function is the function that will execute like this return type is an int, so you can see here it's satisfied, like we're returning a 0. Like normal, like we can also like return -1 or whatever number we want, but the convention for C is that returning a 0 means successful execution. Like if you've ever using a C and then you call a function and returns -1 or it returns 1, that means something fucked up and you should take a look. No, like this is the integer data type, so you could like this will compile, like this will be fine. But normally it's just 0, right? And then so all this function does is just prints hello world back to the console. And then, so yeah, let me show you what happens if we don't include this line. So yeah, not like, let me split my screen. So normally, the way that you compile this is you GCC main.c, right? And then it'll produce like some output file, but this is gonna give me an error. Because implicit declaration of printf. It's like it doesn't know what is here. So you need to include standard il.h, and this just this has the function definition for printf. So if I do it again, we're gonna see it produce an a.out file. So you can like open it, but this is just, this garbage. It's a binary file. This is what your CPU can understand, but when you try to open a text editor, it's nothing. And then when you try to run it, so like when you run something in Ubuntu, it's like that. You do like a slash, and then let me pull it out a bit more. Okay. So it looks like a.out, like \a.out to run it, and then as expected, it just prints hello world. So I'm gonna remove that a.out, but we can also like GCC main.c -o main.out. So this just means your output file, I want it to be called main.out. Then if we look over here, right, there's a main.out. So I'm just gonna call it like this. Just because I don't want it to be like a.out, that to be main.out. So let's take a look at the steps. So the first step when you compile a C program is expanding the header files. So there's like 3 or 4 steps that happen before we produce this a.out file. We can actually stop GCC at one of the intermediate steps and take a look. So that's what I'm going to do. I'm going to do GCC -e. -e is the command that stops that just expands the macro. So GCC dash, and then I'm gonna call it main_expanded.c, because this is still a C file. And then it happily compiled, no issues. And I can open it up here, and you're gonna see, like what is all this stuff? Like all this random stuff that happens. What happened is this line include standard il.h. What it really means is copy paste all the contents of the file standard il.h and put it here. So like standard il.h is on my computer, it's stored here. So I could ls/ or let me do a right. So this is this user includes standard il.h, and then this is the actual file. What just happened here is it's gonna copy paste the content of that file and literally just like dump it here. So this is all standard il.h stuff you can see, and then at the very bottom you're gonna see our code, right? So like here. So the first step is pre-processing. Yeah, this step is called pre-processing. One of the things it does is expand macros like this. So let's get it a little bit more complicated. So I'm gonna create a new file called main.h. And this is gonna be the header file for our main file. So over here, I'm just gonna define the function int main void. And then I'm gonna include it here. Include main.h. Like notice the quotation marks changes because this is like a custom file. So yeah. So and then we can go back to our prompt here, just clear it. So GCC main.c -o main.out, and then nothing has changed. like we can run main.out and it's gonna print hello world. Right. So now with main.h, I just want to show you that we can do like we can do other fun stuff in the preprocessor step. So you might have seen stuff like this, define user constant 5, right? And then I'm gonna add an additional line here that's printf right, yeah. So let's run the -e step as well, so we can get a new. So we've included main.h, and then main.h I've defined a macro called user constant, and I defined the value to be 5. So magically, like this you see is not highlighted in the syntax, but like this is going to get replaced with this. So in the preprocessor step, the preprocessor is going to go, hey, I know that constant is defined here. I'm going to take this and literally copy paste it here. So that's what the preprocessor is going to do. I just want to show you that. So GCC -e main.c -output main expanded.c. So I just ran that, and this is the expanded file. And you can see it like exactly like the main.c that we had is called user constant, but when you run it through the preprocessor, it gets replaced by 5. Right. So that's one thing. So preprocessor, it expands include statements, expands macros, and then this this is like another macro you could do. Square. So like this is a function. This is a one-line function that says if you square something, it's gonna actually replace it with r times r. So like let's go over here. So make a new thing that says printf, or doesn't even need to be yeah. So what do you think is going to happen now? So user constant is a macro, and then square is also a macro. Sorry? Yeah. So let's run it again. So I'm just pressing the up arrow on my keyboard. That goes to the previous command. So GCC, same thing. Then we look here at the very bottom. It's replaced the. Let me just yank this. So this is the original, right? This line right here, and then it's replaced it with 5 times 5, right? So this got expanded out as well. So that's the first step, pre-processing. So now we have this file that exists in memory. Normally during regular compile steps you won't see it, but it's here. And then the next step that happens is generating the assembly code. So we can tell GCC to stop at that assembly stuff using the -s flag. So GCC main.-s for assembly, main.c-, then I'm going to output it as main.s. The s is usually the file extension for assembly files. So it's going to create a new file here, and then we can take a look. Yeah, so this is assembly. This is like as close to the human readable form before it can convert to something that the machine can only understand. So this assembly more specifically is Windows or x86 assembly. Like these function calls are specific to the x86 instruction set. If you try to convert this into something to run on an ARM processor, it wouldn't work because these things don't exist on an ARM processor. So smart people, which I'm not, you could compare it. could do like a side by side here, and then people could tell you like, oh yeah, this section of the code got expanded out to, you know, the steps. But I don't want to do that. In second year and third year courses, you will be forced to do that, especially in ECE. So I'll leave it at there. But like just so you guys have some feeling for it. Like I think this is like a comparison operator, I think. So like less than or equal to or something like that calls a function move, like this is move L. This looks like a move register step. So it's putting like 25 into some register here. So like that's kind of how you would read through this assembly step. So and then the last step in the GCC compile process is producing an object file. So we can do GCC-C main.c-o main.o. So object file is .o. Did it produce it? Refresh. Oh, I guess my Sublime text doesn't want to show object files, but it's here. And if we just take a look, what's in here, it's a binary file. I'm gonna force it to open it. So yeah, so you can see like there's kind of text, but for the most part it's garbage, right? And then this object file, the .o file extension, is then compiled into the actual thing. So GCC main.o main.out. I think this will should work. Oh, I produced. Oh, this is my bad. Should be -o main.out. So now the main.out. Yeah. So this is the whole program. So to recap, I guess I can use this as notes. So number one is pre-processing. So this is include header expansion expand macros. And then the second step is assembly. Convert to a .s assembly file. And this so at this point, this is machine specific or like architecture specific. Like if you had an assembly file generated for ARM, you couldn't go back to something that was for a Windows PC. And then the last step, the step here was compiling. So this is like producing object files, x.o. So what if we had some more things? So what if we had a new file here called like I'm gonna call it fib.c, and this is gonna be a very simple like Fibonacci recursive thing. So like I've typed it out so many times that it just kind of comes. So you can just follow along. If n less than 2, return 1, else return fib n minus 1 plus fib n minus 2. Then I gotta put my things here. Yeah, so this is another file that computes like Fibonacci numbers. So the usage will be like fib5 and then this should return like 8 or I don't know, whatever the 8th Fibonacci number is, right? And you want to use this in your main.c. So how do you do that? Well, to start off, you probably want to have a header file for this that you want to include. So I'm gonna make a new file called fib.h, and then I'm just going to put this header there. So yeah, and then up here I'm going to include fib.h, right? So everybody there? Or do you guys need to see this function or? Yeah.
I'm good.
Okay, I'm gonna assume people are good. So let's take a look at what the preprocessor did to this file. So we are going to go back to our preprocessor one. So GCC-E. And then again, we're gonna see what's up here. Go back to single view names. Okay, so this is the function, and you can see all that it did in the preprocessor step here include fib.h. Like it just took the contents of fib.h. It just took this, copied it, and just pasted it like that. And you can see it over here, like it's just copy pasted the file. Okay, so now we should be able to do something like print the first 10, or let's print the first 30 Fibonacci numbers, right? So for int I equals 0 equals 0 equals 0. Why is my keyboard messed up? Okay. I less than 30, I plus plus. Printf fib percent. I think 6 should be enough. So so does this line of code make sense to people? So we're printing, like the print output will look something like this, fib 5 equals, and then I put 6 spaces here, so actually it'll look like there's like a filler space here, and then it'll be like 1 2 3 4 5. I don't know what the Fibonacci number, like 13 maybe. So like this is just what the numbers here mean, just have spaces. And then the first argument gets I, the second argument gets fib I. So yeah. So let's just run it normally just to prove that it works as expected. So GCC main.c, like that, like in a class, that's like all you would need to do. And then I'll rename it to main.out, right? Undefined reference to fib. Oh no. But it's there. Oh. Probably no. What's wrong? What's wrong here? Well, okay, I'm gonna go through the steps more line by line, and then maybe that will fix it. So GCC fib dot. I'm gonna produce the object file for this. So fib dot c dash o fib dot o. So this will produce an object file. Again, remember the object file was the thing that looked like binary. So here is the object file. And then I'm also going to produce the object file for main. So GCC main. The -c flag is compile. So again, compile is producing object files. -o main.out. So now we should have 2 temporary files, and O and this, and then now we can compile. We can link them together. Actually, yeah. So GCC actually in the background calls a function called LD, or yeah, like it's stored here. This is the GCC linker. So I think I should be able to do this. Fib.o dash o. So this is just linking the 2 files together to produce 1 file, because like we've compiled both steps and we need to put the 2 parts together. Do I have a syntax error somewhere. Maybe let me just replace this with GCC. Okay. And there's an error somewhere. Do you guys see it? I don't see it.
I don't see anything.
Okay, this is, I'm gonna cheat. I'm gonna go back to my demo folder that I had before because this was all working. I'm gonna see what is different. Oh, is it there? Just give me a second. Oh, okay, yeah. Okay, I just called it wrong. Try demo. So the correct one should have been like this: GCC -c main dot h main dot c dash main dot o. So I'm producing the object file, and the object file actually needs both of these files. What is going on? C flags -g dollars. What? I'm just experimenting to see why this is acting up.
Do you have to include fib.h in the compile as well?
I don't think so. Okay, I don't know what happened, but the recipe worked. So this is oh sorry, this is my fresh folder. So starting from nothing, we create the object files for main.o. So like in creating the object file for main.c, because we call it an include here, it's gonna grab main.h anyway. I think that's the reasoning. So and then we do the same thing for fib.c. And then now we have these two object files. So these this one and this one, and you can see they're like kind of big. Like I think this is in kilobytes, or I'm sorry, this is just in bytes. So they're like, if you compare like fib.c, fib.h, they're like small files, and then fib.o is like really big. So that's like a clue that we're on the right track. And then we have to link them together. So again, GCC main.o, fib.o, and then dash main.o. So we've now linked them together, and then we can run, and then it'll, I guess I forgot the new line thing here. So what I wanted to say is that when you just have one file, when you have just one file, these steps are enough. You just compile it, and then because you don't need to link any object files together, you're like done here. But like so if multiple files, we need to link their, this is called the linking step. We need to link their object files together. Okay. So and you can see how this will expand. So like imagine you had let me just show like my GitHub of something. GitHub spaces this one. So this is like the compression project that I've been working on. So I'm just going to show you what this would look like. So you can see like a .c.h files here, and then there's there's a helper.c and helper.h, and you compile that into a helper.lib.o file, and then you would have a compression.o file and link them all together. And then this can also be in like subfolders. So like in here, there's a encoder.c and encoder.h that both get compiled. And then within this folder as well, there's even more stuff. So this idea of producing individual object files and then linking them, that's applied generally. And then the last thing that I want to show you is if you compile with debug options on, then you will be able to use the GNU debugger. So I'm going to quickly recompile everything. So GCC dash, I'm going to use -G now. -G means compile with debug symbols on. Okay, so let me show you what like it would look like. So gdb main.out. So gdb is the GNU debugger. If you try to run it here, it's going to say like no debugging symbols found in main.out. So we have to recompile all our code with debugging symbols on, and then we should be able to use this. So it's Q to quit here. So GCC-G, again, the debug symbols, -C main.c -O main.o. And then same thing here, but for fib.c -O fib.o. And then main.o fib.o And then, yeah, I also fixed the spacing thing. So we should get this stuff. So now we can do gdb main.out. And then it's going to say like, oh, it successfully read the symbols correctly. All right, sorry, was I going too fast? Are people at this step?
I'm good.
Yeah,
So you have something that looks like this.
yes, moving symbols from the other.
Yeah, okay. So I'm going to show you like, so GDB is a command line interface. You can do something like put a breakpoint at line 10. So it's going to be break main.c 10. This means put a breakpoint at line 10. And then you can see the breakpoint is there. So info breakpoint. This will just show you all the breakpoints that are available. So it tells you some more stuff that you kind of can ignore, but yeah, there's a breakpoint on line 10. And then R to run the program. And then it's going to say, oh, like I hit the breakpoint. We're here. So we could do backtrace. Backtrace just tells you like what is the stack. So because we're only one function deep, we're only here. And then you can do like this is like list as well. So like list 10. This is where we currently are in the code. So we're stuck on this line. And then I can print next to step onto the next line of code. So like I've just exited here, and now I'm at top of the for loop again. So I can do next, and then continue through. And then you can see like in between these functions, this is the print output of the program that is just interspacing between. You can also do like info locals, and this will give you information on all the locally defined variables. And then you can, so info breakpoints, you can also disable. So this breakpoint, we only have one, it's numbered 1. So we could just do disable 1. And then info breakpoints, you're going to see that this is enabled or disabled. This is enabled, it's saying no now. So if we continue through the program, then it's just going to go through the rest of it, and it's going to exit normally. And then you can like run again. So I'm going to use the shortcut for breakpoint. I'm going to put a breakpoint in fib.c on line 6, for example. Right. And then we can continue, run the program, and then do a backtrace. And this time the backtrace is actually 2 levels deep, because we started in main. Main actually called the function here. So you can see this, there's like two stacks here. So this, I'm showing you this GDB thing because in STM32 Cube IDE, there's like some functions up here that are like magically stepping through the code. And I just want you to know that that's not magic. This is in the back end. This is what's happening. Cool. So that concludes like the first part of it. I hope you were able to follow along and see some things that you might have not seen in class. Yeah, any questions?
For the example you showed us on GitHub, would you have to separately make all those object files and link them together?
Yeah. So I think you bring up a really good point where like I don't want to be, so I'm gonna quit out of this. It's like, oh, you're still active, so I'm whatever. So we quit out. So I don't want to be going through GCC, like calling this a bunch of times. The way that programmers before us solved this is they would create something called a make file, which is file that I opened here, and it will automate away these steps. So like this step is like if I expand out all of these definitions, this will look like GCC main. Okay, this step, this one, because I'm producing the object file, right? So this step will look like GCC dash G dash C main dash C dash O main dot. Like this is what the main dot O. These two lines are equivalent. So, and then once you have this make file set up, I'm just gonna go back to with that folder. So go back. So now you can see that there's a make file here. I could just call like make all, or we do a make clean. So this will remove any fragment files, and I can just do a make, and it'll do all these things in sequence for me, right? And then I've also defined a thing down here, make explicit, so it'll show you all the things. So make explicit. This is called a target, by the way, and these are dependencies. So I'm running the make target called explicit, and then it's gonna produce like all of these files that we could look at. Right. So this is like a level 2 thing where you can do some stuff. So does everybody like any other questions?
Yeah, actually, I have one. So what's the kind of not difference, but what's the value in learning through like the terminal commands versus using an IDE like VS Code?
It's because at some point when you use an IDE, it's going to give you a weird ass error that you don't know how to solve. And when you have this deeper knowledge, you're going to be able to say, oh, I should probably change this in my IDE settings. And then it'll fix the problem. So like I think Cameron can attest to this. Sometimes the STM Cube IDE will be like, cannot find object or linker failed or something. And like that should give you a clue that you need to change the settings in the compile steps. So let me just show you. Project, I think here. Yeah, so that should give you a clue that you need to change some steps here. Build set debug. No, this is not it.
Actually, no, I think you have the right menu. Go back in, properties.
Oh, I was in the right place.
Yeah.
Let me just see these properties. Is it nothing showing up? Whatever.
Yeah, and then under C general, it should be paths and symbols.
Oh yes. So like all of this stuff is equivalent to command line arguments. Like I'm sure in the backend it just converts it. So if you get a weird ass error in STM in the IDE, you don't know how to solve it, having that background knowledge will enable you to change these settings with confidence to solve the issue.
Gotcha. Thanks.
No problem.
Any other questions?
Well, I guess if you're running something from terminal, like do you have to do, and you have a make file, do you have to do make and then like / whatever, like every time you change it?
Give me a second. Sorry, what make / sorry, like make or what, something like that, or like
No, like run make is a command and then / or yeah, on the project, I guess. Never mind. Maybe that doesn't make sense. I guess my question is, do you have to like invoke the make file every time you make a change? Like you have to recompile it, right? But if you already have a make file included in the project, can you just run it? Or will that not work?
so makefile, like just think makefile as the doing all those GCC steps, but like automated away. Like it's not, it's the steps to build something. It's not actually the thing itself. So like we do like make clean make.
No, yeah, exactly. But you have to like do the command make on your project and then every time you run it, right? If you make changes. Yes.
Yeah, that's right. That's right. And
Yeah,
like
yeah.
another thing with make files, it's like it's smart because like so the situation is you have 100 different object files that are used by the project, but you make one change in one object file. Like make is smart. It knows that you didn't edit the 99 other object files, so it's not going to recompile them. So like just to show you that it's working. So I only edited, I don't know, like fib dot, like, let me just give it, so this is like, it's not going to do anything, but I've changed fib.h. So if I do a make call, you can see that it only compiled fib.c. It didn't compile main.c, right? It just reused the object file that was there. Yeah. So they, like, I guess they don't really teach you make files in school. You just gotta learn it because everybody at work uses this. So you just feel left out, like, okay, I gotta learn this stuff. Okay, so like, I guess we're good. Any other questions? And then we'll transition to the STM32 cube side of things.
One question. This might be very like high level for this tutorial, but like, how does make know that it shouldn't compile another main.o without actually compiling any comparison?
The timestamp on the file when you saved it, when you last saved it.
Oh, okay, okay.
Okay. So let me. I'm going to change the make file. So this is me like an hour before here. So well, we were using GCC, right? So we were doing like GCC and then like whatever to do stuff. GCC knows that you're trying to run it on your own computer. So your computer is going to be an x86 based computer architecture. The new MacBooks will be like the ARM, whatever Apple architecture, right? So so here's the situation, right? Your computer is an x86 architecture, but when you compile the code, you want to run it on another computer, aka our devkits or our microcontrollers. The microcontroller is an ARM architecture. So now we have to do something called cross-compile. So use the x86 computer to compile for a machine that's not x86, that's an ARM architecture. So for that, you would use another GCC thing. You would use, let me just show you the web thing. So like you would use the GCC ARM toolchain developed by ARM, and there's a download page somewhere. Yeah, like you can download this stuff. So if you're using Ubuntu knows that this is a really common thing that people want to download. So they've wrapped it together in a thing called bin utils. So this is binary utilities. So sudo apt install, and this will be like gigabytes, like huge, by the way. So you can go ahead with that if you want. But this will give you the ability to on Ubuntu compile for ARMs. I've already installed it, so you're gonna see that there's nothing that I have to do. So to save you the effort of installing it, I'm just gonna change these 2 lines in my make file, and now all the compile steps are gonna be happening for ARM GCC. So like this is let me just show you. So this is all the things that binutils came with. This ARM is the manufacturer. None means it's not specific to any operating system. And then this one means embedded application binary interface. So I'm going to be using the ARM non-EABI GCC. And I can do like a help, and then it's, oh, I guess it just doesn't want it. Yeah, so like this is a thing that exists, and you can do a dash version on here to see it. So I'm gonna make clean. So I'm gonna do a side by side here. Oh wait, give me a second. I want to save the old files as well. Just whatever. Okay. So I'm gonna open up the main.s as well. Okay, so here's a side-by-side view. I just want you to observe this is for ARM, for the ARM. This is assembly code generated by the GNU ARM GCC none thing for an ARM processor, and this is the assembly code. And this is the same thing generated, but for my own computers, for x86 computer architecture. You can see that like push, add, like these are registers that like it's different. Like the registers in x86 are like prefaced by this %sign, whereas here it's just like, I think this is file pointer, stack pointer, register 0, register 3, so on and so forth. So I just want to show you that, it like they're not interchangeable. Yeah, so the steps are the same. You would generate an object file. Where it differs is you would take those object files and put them all together into something called an ELF file. And then from the ELF file, you need to generate another file that's compatible with your programmer that you're going to use. So let me just grab devkits now. Okay, so like this dev kit, I don't know how people are gonna see. Okay, this dev kit, this is the ARM CPU, and then this is the programmer, or like the top half of this board is the programmer. So we need to compile the code into a hex format, and then upload that hex file to here, and then it will know how to run it. Did that make sense to people? We're compiling the code into something that this can understand, and then we're taking that version of the code. Okay, let me do like more notes here. Maybe this is better. So like, oh, where was my notes page? Over here. So like step 5, right? So like, I don't know what it's called, but like you produce one ELF file that has everything on your program. So like combine all the object files into a single ELF file. And then 6 is like convert the ELF file to a format that a programmer can use to upload to the device. So like an ELF file, when you open the binary file, maybe like 00001, 000. So like converting it to a hex format specifically, it get like one of the optimizations that it does is it gets rid of those zeros. So when instead of saying 00000, it's going to say 11 zeros and then a 1, 12 zeros and then a 1. So like this the difference between an ELF file and a hex file. So like literally the file will be like main.hex or something like that. And then that hex file is then what your program can understand. That is what your programmer can understand. And then your programmer is gonna like then decode that like hex goes to here. It's gonna be like, okay, I'm gonna strip away all that thing and expand it back to just a bunch of zeros. And then that's gonna go to your microprocessor that's gonna run.
Right. So the output goes out, that's still on your personal machine. And then the out goes into the program, which turns.
You produce the hex file on your computer as well.
Okay, so
Yeah.
the bridge is like between the hex and
Yeah,
the thing.
goes to be uploaded. Is uploaded to the programmer.
And I'm guessing different programmers, like this one reads hex. I'm guessing other programmers don't read hex, which
Yeah.
is why we need the out file. Instead of going straight.
No, hex format is actually like kind of ubiquitous now. So like there's other things as well. Hex. So like, yeah, the Intel Hex 32 is a standardized format that almost every programmer uses.
Right. Yeah. Then what's the point of the out file? Instead of going straight to hex.
Because the hex is like an optimized ELF file you can think of. So yeah, like I don't know. This is I guess yeah, you can think of it like that. Like I don't think I have enough knowledge to be able to answer you deeply because these decisions were made in a smart room back in the 1970s. So yeah. Yeah. So let me run you through something. All right, I'll run this one. So give me a second while I close all these other projects. So this is a good time to start opening up this IDE. So it's like STM32 Cube IDE. If you have it installed, just open it. Close projects. Oh my God. Oh. I guess also this is another reason I don't like using IDEs because they're very clunky and slow sometimes. Like I'm just closing files that is taking a long time to do. Yeah, so like does everybody have this open? I want you to grab this Git repository and then install and then open up that file because that's where I've kept it. So I think you can just download as zip here. Where's my Zoom window thing? Chat. No dark mode. There is a dark mode for the IDE, David. It's just I don't like to use it. I think it's maybe in preferences, but yeah, there is a dark mode. Appearance. Yeah, here you can be happy. Here's a dark mode, David. but I'm not gonna use it. Yeah, so please just download that whole Git repository, and then the one that you actually want is this one. So like let me just go along. So download zip. I think this is gonna be a pretty big download, but whatever. Put it in my downloads folder. Okay, and then like unzip it. Yeah, let me just close my STM32 cube IDE, like, so I'll follow along exactly as you are doing. Okay. So unzip it. I assume you guys are here already. And then from here, open projects from file system. And then navigate to this folder. So stock LED pattern. So you can just grab here and like Control-C, like copy that whole thing, like if you're on Windows. So copy the file path and then I'll paste it here. Yeah, and then it should automatically recognize that this is a project. Are people there?
Yep.
Yes. Are you confused? Okay, we can take a look after.
I also clicked finish, is that a problem?
No, yeah, that's fine. Go finish. So you should be able to see like in your sidebar, like this thing. So you can drop down and then just open core source main.c. This is the file that actually matters, right? So once you're here, you should be able to see this little button here. It means build. So you can go ahead and click it, and it's gonna show you stuff that should look familiar. Let me expand the console. Cool. Here we go. Okay, so I just detached the console and you can see like, oh, it make, we've seen make before, right? So like make J8, this just means my computer has 8 cores. So make J8 means you run make using 8 cores, and then like make all targets, right? And then you can see make is actually calling the same things that I was calling before. But again, there's just a ton of other stuff here that we let the IDE deal with, and it hides away some of the complexity for us. But like this is, like at the end, it's produced an ELF file, and it's also produced a hex file as well. So this is just a build step that's doing everything that we can on our own computer before we upload to the programmer. So let's upload now. Here you can. And I think deny is, yeah, so yeah, so you connected to the power, the one up. Yeah, because there's also another one down here, but that's not gonna work. Okay, so I am connecting it to my computer. When people do this, you can confirm that it's there. By number one, it's going to open up this. Like it looks like you've inserted a USB drive. Like this is a very fancy thing that has like Windows drivers or whatever, so it can pop up this window. Most of the times when you use a programmer, you're not gonna get this. So open up a device manager. I guess I'm literally just talking to Oren at this point. Yeah, or and Mark, because I know you have a dev kit like beside you or something. So device manager, and then open up COM ports, so ports here. And then you should be able to see so it's taken up COM port 6. It can take up like 1, 2, 3, 4, 5, like whatever. It just happened to take 6 this time. So STM microelectronics ST link virtual. Yeah, so this is it's detected. So over here we can go to this debug thing. This debug, select the drop down and then debug as STM32 application. So just hit that, and then things should be happening. Yeah, cool. What happened? Yeah, so internal error, what is going on? Anyway, so you should be, are you here or screen that looks like this? So let me exit out of here. What's this? It's debug as, and then new. Thank you. So this is like a one-time thing because you've never done it before.
I have debug as STM32.
Yeah, that one. How do I get this to like go back? So like, what is going on? Okay, so do you get a screen that looks like this?
Yep.
Okay, so on the left side here, this is your stack trace. Like again, when I was using the debugger, you have your back trace. So you can see like, this is the project. This is the ELF file that was loaded. We're using core, the first core, the first thread of the first core, and we're on main at line 156 right now. So, and then you can, like, this is step over means next line. So it'll go, now we're on this line of code. Now we're on this line of code. So like, think back to the GDB example, we can step through lines of code. This is just a much fancier way of doing it, right? And then if you just hit the zoom button, like, so this will just run continuously without any breakpoints. And you should be able to see that it's blinking in user LED. And then when you click the button again, like it's a blue button, it's gonna start blinking another one. And then click it one more time, and yeah. Do you have a PuTTY or some other terminal thing installed? Do you have? Okay. If you don't have anything, then install this. Cool term. It looks like a really sketchy install, but it's like it's legit. It's on the left side here. Or did you wait? Are you on this website or Roger Mayer's freeware?
Oh, no. Software.com. Oh.
Just I use Google and it's the first one here.
Stupid thing. Yes.
Yeah. This one, and then just download it and run it. I already have it installed, so I'm just a few steps ahead. This is a terminal that talks to this. So it's a different. You can use other stuff, but this one has nice features, so I like to use it.
Oh.
Okay, do you have this open? Or, yeah, I do. Yeah, allow it, it's fine. It should be just a program that you could find on your Windows thing. We're watching Oren install. There it is.
I'm doing it there, yeah.
I don't so let me show you the line of code. So like there are two two lines that are talking back and forth right now. One is TX and RX. So one is the transmit TX and one is the RX, so receive. There's a TX line that goes from here through the cable to your computer, and then there's also an RX line from here that your computer's TX will send. So the TX and RX are like that way. And they toggle at a certain rate. So this is called the baud rate of how fast those bits are changing. And we need to, on both sides, we have to set the correct baud rate or else it's not going to understand. So in the project that is running right now, if you just scroll down to the USAR configuration, you like the baud rate was configured at this speed, line 395.
Yeah, 115.
Yeah, so we go to cool turn options, baud rate, and then just select that. So it should be the second last one. And if you have multiple devices, then you're gonna have to change your port right now. But like we only have one device plugged in, and it auto detected as port 6, so we're good. And then all the other default options are fine. So here, and then we hit next, and then you should see some debug messages back. Are you the OK button is off the screen. And then resize the window. And when you resize the window, that's annoying. Yeah. I'm just gonna hide it as far so we get more screen real estate. Okay. And then hit next. Yeah. So this is when I wrote this code, I wanted to send back some debug messages. So obviously we can't like print out and then to terminal and look at it because there is no terminal here. So we have to send all of our stuff back through here. And you can play around with like pressing the blue button. Let me just disconnect. So like I press it a bunch of times and you can see like button press, button release, all this debug stuff. And then like I have two internal state variables that I'm printing out the status of to help me debug as well. I don't know how much detail I want to go into the operation of this program, but in conclusion, I'll just close this. Let's see. Like you would use the auto generation tools to generate most of the code that you see here. So like all of this code is auto generated. The only code that I ever touched was in the main.c file, and only parts of this are the parts that I wrote. I think we might be reaching the end of usefulness for this. So if people want to like if people want to start from scratch and recreate this project, I can happily go through that. But I think the only people who would benefit is like Oren and maybe Mark, because I know you have the dev kit.
What lines did you change? I'm just curious. Like in the while loop, mostly?
Okay, let me okay.
I guess you have to
I mean,
configure some of the
like,
GPIOs and like go back to the map and shit, so that's okay if you don't want to do that.
I'm gonna explain like everything how I did this, because the question of what lines did you change is a little bit more complicated.
Yeah, okay, fair.
So you can please open the ILC file. I think people like just that at home can follow along as well. So the ILC file, I don't know what it stands for, but it's just like configuration file. Like if you just open it in like a text file, yeah, text editor. Like it's just a bunch of like settings. But STM32, because this is their tool, they make it look nice using this configuration tool. So I initialized most of the settings to default. So for example, I didn't mess with the Ethernet or the USART. Like, let me show. So connectivity, scroll down. USART 3. This is the default transceiver receiver thing that we were using to talk between the microcontroller and the computer. When you select a project and select all the default options, this will be configured for you. So for example, I didn't touch that. I didn't touch this. The only new thing that I added was a timer. Timer 16, I guess, as it happens. So I've activated, like I would hit like activate on timer 16, and then the parameter settings that I used are here. Maybe you should look at the clock configuration as well. Okay, so this is, can I make this bigger? Yes. This is a clock configuration screen. So microcontrollers, they need a clock to operate. So this is the same as like, oh, like your computer can turbo boost to like 4 gigahertz. Like it's the same thing. But we're managing it directly. All of the thing that matters is this HB2 peripheral clock down here. Or I think in the manual, it'll say like timer 16 is connected to this clock. I believe it's the ABP2. I can't remember though. And then so we want to set this to a certain frequency. And then you just go up the tree. It's like, oh, there's a prescaler here. You can change this to divide by 4, divide by 16, whatever. Yeah, so, and then you just go up it, and you're gonna see that this we have the H clock, which is like the master system clock. But we have some prescalers down here, and then eventually it's going to get divided by this one to get 64 megahertz. So with the 64 megahertz input clock, we can go back to our timer 16 configuration, and this is dividing it by 6,400. So like 64 megahertz divided by 64. That's 10,000. This -1 is just like an offset by 1 thing that the program, it's like a weird quirk of the program. You just have to remember to put the -1. So this is there's a signal that's 64 megahertz. And then we've used this timer to reduce it down to 10,000 times per second, so 10 kilohertz. That means this timer is going to take 10,000 times per second. And then I've added another counter period to 2,500 minus. Again, just ignore the -1. So this is, if something is ticking at 10,000 times per second, how long is it going to wait to take the 2,500 times?
Quarter of a second.
Yeah, that's right. So this all that work that we went through to with this clock configuration, everything is to generate a signal that will trigger every quarter of a second. So we've enabled this global timer interrupt. So if you go back to the main code now, you're going to see that there's a timer callback function. Yeah, so how timer period elapsed callback. So and we gave it timer 16. So all of that work is to say that every quarter of a second, this function is going to be called by the program. And the reason we use timers is that we can do other stuff in our main loop. So it's like we can have stuff happening in the main loop, and we could pause stuff in the main loop, but regardless of that, this timer is always going to be ticking. This function is always going to be called every quarter of a second. And then here is where I transmit back the debug configuration. And then the way that the program works is like really simple. So every quarter of a second is going to go into this function. The function is going to check like, oh, which light should I be turning on? The red one, the green one, or the like, just figure out the correct one to turn on, and then it's going to like flicker it. So this is to check the correct timer, and then we increment the counter tick. So this state is a button state variable. So like, if you can imagine, this is 0, 1, 2, 3, 4. Every time I click, it goes up. But I want to set it to 1 or 3 configuration. So you divide by 3. So like, if the state is 7, then this state is actually 1. So I know that I should be triggering the middle LED. So it will like 1, 2, 3, 4, like, and then it will be like 0, 1, 2, 0, 1, 2, 0, 1, 2. Like, it will just tick along like that. So if it's 0, I want it to change the green LED. And then this is the toggle. And then this tick is, so if you notice, like the green one ticks very slowly. And then this one ticks a little bit faster, and this one takes a little like at the fastest. So this, like, if this counter tick is divisible by 4, then we change the green LED. So the counter tick, again, it's going to be like 1, 2, 3, like 4 times a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So every time it hits 4, it's going to tick, which is the equivalent of 12 ones per second. And then yellow LED, again, like the same checks, tick per, like divide by 2. This is 1, 2, 3, 4, 5, 6. So twice per second. And then otherwise just change the red LED. So this function is being called every time a quarter of a second. And then in my main, the only thing that I'm doing is, so this is the start of the main function. All this is like some configuration stuff that's not important. Like this is just setting up the what pins to toggle. That's the red and green stuff. The only thing I do is this like check button function. So let's just go there. This is near the top of the code, by the way. So again, this is something that I wrote. In the main loop is just always checking the state of this button. So this button is connected to the GPIO pin. So like if it's 1, then the button is pressed. I'm not going to print back the button is pressed. And then we're going to hang in this while loop forever until it's released. So the state is 1 now. It's still 1 because I'm still holding it down. We're still in the while loop. And then once I release, then it will exit this while loop because it's going to break, and then I'm going to update the state. And yeah, so, or this is all to answer your question of like what lines of code did I change. So I changed some stuff. I called this GPL check like button function. I did some configuration stuff in the main to make my life easier because I don't want to remember like what pins this are. I just want to say that the green one or the yellow one. And then I also did this timer callback stuff that you saw that, it took a little bit of brain power to think through like how we configure it.
But do you need clock if you have like a button press?
So the issue, like, I tried to implement it the way that you're thinking in your head. The issue is that it's blocking. So like when you press the button, the LED like stops flashing. Because like once the button is pressed, you're like waiting for the button to be released, right? So the LED flashing is gonna not change anymore. So we need to rely on some external thing to have two things running at the same time, basically.
Okay, so you're saying like the default flashing and then like you're like hard coding the LED basically.
Like you need to see this. Like, oh my god, my cable's too
Yeah, the
short.
center stage.
Oh, let me turn that off if possible.
Draw a smiley face on the nuclear.
Video effect. Okay, this is like a stable camera, right? Okay, so like the thing is blinking. When I change this, it blinks different. So like if I try to do it your way, I'm holding down the button right now. This would stop blinking, right? Because it's like I'm waiting for the button to be released. But using an external timer callback, this is continuing to tick away.
Oh, you want it to blink. You don't want it to just be like a solid whatever color.
Yeah.
Oh yeah, okay. Okay. And then why did you do the dot pin and the dot bank? Like I don't really like that was just you making that struct, right?
Yeah, that was just me because I didn't want to deal with remembering that it's GPIO B0 is the green LED. So I just, this is a user defined thing as well. This type GPIO type. I wrote this. This is just, it just contains a bank and a pin. Yeah. And like the two things that you needed to toggle the LED.
Oh, right. So those are the two things that like define what GPIO. Yeah. Okay.
So like GPIO, so like this will be equivalent to like how GPIO write and GPIO E and then like GPIO and I can't remember like E12 or whatever, but like I didn't want to do that, so just
yeah, I think the syntax, because it's an embedded function, right? The HAL GPIO write pin, it's like already exists.
What do you mean it's an embedded function?
Like I guess it's like it is automatically like generated by STM, so they like give it to you so you can just
That's right.
arguments. So, yeah,
like
okay.
This is okay, let me show you STM32 H7 how. So this like 3,000 page document, or it's almost 4,000 pages.
That's horrifying.
Right. So this one contains all the information about the HAL or the hardware abstraction library, which is this auto-generated thing that STM32 creates to make your life easier. And if you just go to the GPIO section, GPIO generic driver, you have these function definitions, and it'll tell you like, what to do.
I normally just like trace headers and try and read comments, and it's not as fun.
And like once you work with the STM32 HAL long enough, like you can almost predict what the format is going to be, because there's like a certain style that's consistent throughout how this HAL is written. But yeah, like this is just for the GPIO. There's like so many other things that we could be using, right? And this document is literally just, like page after page of APIs and And occasionally there's some text that describes in detail how you should be doing something. Let me see if I can find a section where it's like that. Yeah, so like, you know, your notes section gives you some more stuff. Okay. Are people confused, or did I take you through a journey that your brain is like, can't wrap your head around? Or like, sorry, maybe I should ask at a different point. Like, at what point did like you just gave up? Like, this is really difficult.
I'm just lucky that I had a few days to prepare.
So wait, so you followed all the way through?
I mean, I got the general idea. There was a lot of stuff that was very new, but I mean, I already know, or I've already had experience with using the STM32 cube IDE and stuff, and like setting clock speeds and stuff like that. So I got the general gist of it.
All right.
My laptop, I feel like I like the second part more. The first part was a little bit all over the place. So the second was then fun.
Oh, I could have organized the flow better. Yeah. Okay. Or like, are people remote? Like Aaron, how much did you like keep in your head? Your Aaron is muted. I don't know if you're still like present. Are they sending texts or nothing? Okay, well, what
I
about
feel
like,
like everyone has such different like levels of experience coming in that it's hard to like, I think it like has different levels of helpfulness for different people, maybe, I don't know. Or it's like introducing some concepts stick out more than others for some people.
like, do you think you could, like Aurora, do you think you could recreate this project, like this project from scratch by yourself? Well, with like Googling and whatever, but like you didn't have this reference code.
So yeah, but that'd be kind of cheating because I've done a similar thing already with a different debug or a different eval board. Well, it was like a custom eval board. It was a different MCU, similar IDE. So probably I've never actually like modified the clock, like you're showing the tree.
The
So
clock
that was
tree.
kind of new. The clock tree. That scares me. But as for
there's
like
an
actually
auto button,
modifying the GPU,
like
Mhm.
there's this auto solve button that I use a lot as well, so it's okay.
nice.
Yeah, like I guess while we're here under tools, there's also this thermal / power consumption page that you can set up as well and look through. So you just turn on various peripherals and it'll tell you what's the peak usage, how much power, like you give it your environmental settings and like how much is it going to increase in temperature. So there's a lot of stuff baked into this one. Yeah, project managers, yeah.
That's pretty cool. So I guess my answer is yes, but maybe would not be yes. But I can't say whether or not it would be if I didn't have the knowledge that I do have, because it's kind of hard to like see things from an like a beginner's perspective. I feel like that's one of the hardest things to do. So, but yeah, I thought it was helpful for me.
Yeah, it was quite helpful for me. I can definitely imagine like a few weeks ago when I didn't know any of this stuff, like I would be very confused about the terminology being thrown around. But yeah, it was very good.
Maggie, did this help you at all? I think the non-EC people just like are gone, is like tuned out. Yeah, so I guess we're wrapped here. This is still recording, so I'll make sure to like stop the recording and put it somewhere nice. But any other last minute questions and stuff? If not, I can look through your thing if you want me to, or you might just be like, I don't need to use this, so whatever.
Yeah, and then,
Okay, if there's no other questions, we'll end here.
Thanks,
I was gonna
Yongda.
say before we end the recording, we should have like a code word so that anyone who watched the recording to the end gets like a free box of Timbits.
Sure, like what do you want the code word to be?
What do I want it to be? I mean,
Yeah, like if someone comes up to you and like yells out like, I don't know, like polka dot pumpkin, then you have to buy them Timbits because they watched to the end of this.
yes, perfect.
Okay, polka dot
Love
pumpkin.
And no cheating. You guys can't just like tell people.
Okay, yeah, I'm cool with that. I'm ending the screen share.
Sick.
Wow. So yellow. What the heck? Okay, I'll hang up the call. Thanks for tuning in.
Yeah, thanks, Yanga.
See ya. Thank you.
See ya.